Sorry, I got caught up reading all the discussion. It's time to recommence here. Lots of great discussion in the Slack. Hopefully people are contributing and reading up on that. Let me introduce our panel that will take us over the course of the next hour. People are encouraged to chime in when there's a relevant point, raising their hand and so on and so forth. I'm going to particularly be drawing from discussion in the Slack though. But first, let me introduce our panel. So obviously we're including Dylan Nelson, our keynote speaker for today, and his wonderful presentation. Other members of our panel include Professor Rongmon Bordoloi from NC State, Professor John Chisholm from UT Austin, Professor Romeel from University of Edinburgh, Dr. Chang-Goo Kim from Princeton, and Dr. Miao Li from the CCA Flatiron. So I think I'm pretty excited about this panel, being able to cover a wide range of topics here. Well, first, Filippo, you've had your hand up since before the end of the talk, so I'll let you throw a question in here.
Thanks. Hi, Dylan. Thanks for the nice overview. Well, I mean, as you know, I mean, we have discussed this many times. My general impression is that supernova feedback in simulations, in cosmological simulations, is still at a very strong level that I'm not completely sure. You have touched it at the end. It's comparable to the observations. But one thing that you said made me think of a rather straightforward way of making this comparison, because you said, I don't remember if it's exactly like this, but something like galaxies at high redshifts don't have disks in the simulations, and this is really becoming clear that it's not true. I mean, only this year there have been 2 Nature papers showing beautiful disks in galaxies at redshift 4, between 4 and 4.5. I was in one of these papers where, thanks to gravitational lensing, we could have a resolution of 60 parsec. And you could see that the disk is very regular, and the V over sigma that we find is 10. And now we have other 5 galaxies with gravitational lensing that are telling exactly the same story. There is a paper coming out really this week on Friday. Please, everybody, look at the archive. So these are super starbursts. They are starbursts, and still, when you look at C+, I forgot to say, you see that the gas is in regularly rotating disk with very high V over sigmas. And this, as far as I understand, is not the prediction of TNG or other simulations. Actually, TNG is probably you are probably the few who did this comparison clearly and told us what the predicted V over sigma are. In fact, we put it in our figure. So my question to you, I mean, in general, it's not really a question, it's a discussion. How do you see that the simulations could produce disks with this type of V over sigma, with in fact sigmas that are of order of 30 kilometers per second, the redshift 4 or 5 even?
So yeah, before we jump in, I remember a few weeks ago, presenter said, I have talked enough, so I'm really going to let the panel handle everything. So Chang-Goo, Yuan, John, Rongmon, Romeel, Miao, you guys have to chime in wherever you want. Filippo, for your question, I think we should talk offline. I mean, so I think it's a very interesting topic, and something that we're actually want to work on and compare with, but I would say not the main topic for today, the disk formation.
Well, but this is related to the feedback. I mean, you're not forming a disk because you have too much feedback. too much outflows, right? I mean, it's not. I don't think it's an unrelated question, but okay, we can talk offline if you want.
No, I don't think it's really an issue of outflows. It's an issue of the inflow rate and whether or not you can sustain a ordered rotation. And I think these are the simple sort of arguments that among others Reinhard Genzel and his group have been very much promoting in terms of the instabilities of the disks and the sizes of the molecular clouds that you can form in those types of systems. And what you're saying, Filippo, I think is right. Is right in the sense that, but it's a very mass dependent statement. It's certainly true that in simulations we produce plenty of nice disks at high masses at high redshift. Redshift 2 and 3, things about 10 to the 10.5 or so are clearly disks. We've done Zoom simulations. Daniel Angles Alcazar had a paper in 2013 where we did Zoom simulations of this and showed that it matched nicely with the V over sigmas that were distribution that was observed in the SIN survey. So it's not that we don't produce disks. I think that the problem is if you look at the smaller galaxies, that's where it's less clear. And I think a lot of that has to do with how much do you think the inflows are stirring up the disk, and how sustainable it is to have a thin disk when you have such high inflow rate, cosmological inflow rates.
Any other members of the panel want to comment? Okay. Thank you for the question, Filippo. I think that theme will be addressed at other points during this discussion as well, as we touch on other topics.
Okay.
So there were several different comments about one of the last things that Dylan you covered, and that is the geometry of the outflows, the angular dependence on outflows and the distribution of the circumgalactic medium. And a few points that were made that I'll kind of throw out there and we can kind of discuss. One, is it clear, because I've seen a number of different observational studies, that there is in fact an angular azimuthal dependence on the distribution of the circumgalactic medium and its properties? Oh, thumbs down from Jess. Are you saying there is no azimuthal dependence, or are you saying that's a poor question?
Well, Nicholas Boucher is here, and he said there is, but I've seen like 3 separate results recently that say that there's not with some of the absorption line stuff.
Okay, well, first, let's say one thing. What do the simulations predict? And then we'll talk about what in reality is happening and how we can, broach these two regimes. So, simulators on the panel. What do your simulations and what do the simulations of colleagues in the field show? Is there an azimuthal dependence? Do we see more high metallicity gas in the bipolar regions out of a galaxy? Does it depend on the mass scale? What do we see in the simulations? Miao, you're on the panel.
I'll just do a very quick comment. Oh, sorry, Miao, go ahead.
Oh, no, I'm just going to say, well, it depends on several things. So we find out if it's a fountain flow, then it's more or less more spherical. If it has high entropy and it naturally wants to break out, and the pre-existing gas let it break out, then it is bipolar.
Okay. Dylan?
I was just going to comment. So this plot was very brief, apologies for that, from the Peru paper, which shows the expectation for the metallicity at 100 kiloparsecs, say, versus angle around, say, star-forming galaxies at redshift 0.5. This is kind of our target. There's a lot of scatter. So we expected that this would be a difficult signal to find, and there's a figure in that paper which shows a few data points, and I think it's clear that this scatter in this relation is large enough that you would not see it unless you had a very clean sample. Because, for instance, the dependencies on stellar mass or on impact parameter or on redshift are enough to completely wash out the signal if you're not careful. So I'd like to hear more about
but this is primarily
signal, what it is.
In density. This is in metallicity of the gas. This is in a particular ion that you're seeing. What what are the properties where this signal exists?
So we were mainly focused on metallicity as an observable,
Okay.
but this indeed is total gas metallicity. So we did make one cut in the direction of observability, which is to restrict ourselves to high H1 columns, right? And there the signal gets even noisier and with even more scatter, but it's still there. So we didn't do, for instance, the magnesium-2 signal, but rather total gas metallicity, but it should still be there also in neutral gas or cold gas.
And Romeel has a response.
So yeah, so I just wanted to make a couple of points. So I think this is a very ion-dependent statement. One of the things, so we looked into this in Mufasa. We never published it with Kate Story-Fisher, but you can already see what anticipate what the results are from Amanda Ford's papers, and that is that oxygen in 06 tends to have been deposited very long ago. So this is not recent stuff, and it's volume filling, at least in our simulations. And as a result, we don't expect any azimuthal dependence if you look in that. However, magnesium-2, at least in our simulations, tended to be inflowing gas, and the inflows tended to occur along, of course, the whatever you call it, the major axis of the disk, along the plane of the disk. It's not a perfect thing, but I think that in that case, you would expect, if you look at some of these lower ions, I think you would expect that from the simulations. Yeah, this is at redshift 0. Well, low redshift.
Yeah. And just as something I can add, I looked at this in the fire simulations as well, and we saw kind of consistent with what Dylan's saying. We looked at magnesium-2 ionic column densities, O6 column densities, carbon-4. We saw a slight effect, azimuthal effect, where you'd see more of the metal lines in the semi-minor axis along the like bipolar outflow direction, but it was very slight. And I'm not sure that it wasn't consistent. There was a lot of stochasticity from one halo to the next, so I'm not convinced that this is at least that the fire simulations predict this sort of behavior. But the observational side has a lot more to say. We've got a number of different observers, two of which are on the panel, Rongmon and John, and Nicolas Boucher perhaps can all comment on the observational prediction, because yeah, in my mind, what I've seen from the observations, one paper says you see it, one paper says you don't, depending on the ion. Even the same ion, you get conflicting results. So what do people have to say? Rongmon first.
So again, this is a very phase dependent as well as geometry dependent statement. You have to be very careful when you select your sample because it's very easy to get bogged down with projection effects. If you have a clean enough sample and a big enough sample, and again, the statement is only for cool gas traced by magnesium-2. I showed way back in 2011 that if you take thousands of galaxy stacks, we do see an azimuthal dependence at close impact parameter of 40 to 50 kpc, that you see enhancement along a minor axis for magnesium-2 absorption in the CGM. This is also verified by SDSS survey of thousands of quasar spectra, which is led by Ting Wen Lan, and I think the recent paper that Dylan showed also. They see a slight enhancement along the minor axis. If you look at quasar absorption lines, which historically has been done, Nicolas would probably talk about it. They also showed that, and Glenn Kapchak's group, they showed that, in magnesium-2, you see a bimodal distribution in quasar absorption line. The number of pairs is smaller, obviously, because these are much harder to observe, but there is a signature. But if you go to higher ions like carbon-4 or O6, we don't tend to see anything. We tried to do it with cos halos, but unfortunately the sample size is small, and it's just, the distribution of pairing is not good enough to make a statistically robust statement as yet.
But also, Rongmon, as far as so the magnesium-2, you see it, right? But then that same sample that Glenn Kapchak showed and with Stephanie Poynton, right? They did the actual ionization modeling, and it's not a metallicity effect. So I feel like the magnesium-2 can't distinguish between temperature, density,
Yes, the statement is of azimuthal asymmetry. That exists. The second statement, I would argue, if you observe, again, down the barrel studies, A lot of people have shown in SDSS, Tim Heckman's group has shown, I have shown, as well as Kate Rubin has shown. If you look at face-on galaxies, where you observe down the barrel outflows versus edge-on galaxies, where it should be perpendicular, you do see stronger outflows in face-on galaxies. Again, you have to be careful to have good, you know, like very good disk-only, like disk-like galaxies. If it is irregular, it's not good enough. But we do see signature in magnesium too. That's a limited statement of me.
Okay. All right. The plot thickens. Nicolas Boucher.
Maybe I can add something.
Your hand up.
So maybe on the simulation side, following what Romeel said, we looked in TNG with a student at Columbia, Daniel De Filippis, and indeed the magnesium-2 is present only on the major axis in the TNG simulation. So comparing observations and simulations sometimes is difficult because it seems like the phases are not completely accounted for. As Rongmon said, observationally, I think with all the background pairs and background quasars, there's strong evidence that the magnesium-2 presence, I'm not talking about metallicity, but the presence of magnesium-2 is non-isotropic. So on the minor axis and the major axis, you have an enhancement. And Kristen Martin showed that in her group as well. Now, in terms of the metallicity, it's something that is a signal in Freaker or Dillon's paper that's relatively weak. It's 0.3, 0.5 dex or something like this along the 0 to 90 degree angle. And it's not easy to see, and you need to have a very homogeneous sample. And I think we do have that with a purely IFU-based selected sample when we have this kind of signal that is showing up now. And I would like to also point out one key difference that in between all surveys and other surveys with background quasars is that sometimes, and even the CAPSAC sampled in MAGICAT is a sample that is continuum-based selected. So they take the quasar field, the image with multiband HST, and then they do the spectroscopy on the continuum-based galaxies. And so you have to do a pre-selection on continuum. With IFUs, you don't. And with MUs, we found that 30 to 50% of the O2 emitters that we have no continuum to the depth of the MUs, deep MUs observations. So I think you have to be careful when these things are happening, a discrepancy between different groups here. There's a clearly difference also in the selection function.
Okay, that's fair. John Chisholm.
So I was gonna, back it up just a little bit. And Dylan was mentioning how the azimuthal dependence is halo dependent, and there's a lot of terms in there. But one of the interesting things that I took away from your talk, Dylan, was how AGN, the impact of AGN on this sort of metallicity azimuthal variation can be pretty strong. On the same token, how we implement AGN feedback seems to be pretty uncertain still at this moment in time. So how much can the implementation of both AGN and star formation feedback impact our kind of inferences on these azimuthal variations? Was my question.
Maybe again, just a very small comment then. So one of the, I think, great strengths of the Peru paper is that we actually found the same signal, literally, to within less than 0.1 dex between Eagle and TNG50. Now, those two simulations have enormously different physical models for feedback. I think that's a fair statement. They have substantially different numerical resolution, and they run with very different hydrodynamical techniques. I mean, they're quite different. So we're all, of course, in these kinds of projects, we're always searching for model invariant predictions, right? These are the strongest. If something is actually true in 3 simulations and not just 1, that's for the best. And so it seems that this particular azimuthal angle dependence of the metallicity around star-forming galaxies is quite a robust current prediction from models in general. I don't know, maybe Romeel agrees or disagrees, but that's a good thing.
Well, I have a related question, and this is just exposing my ignorance about the feedback implementation in those 2 models. In Eagle and in Illustrious TNG, for your AGN feedback models, are they intrinsically bipolar, or are they isotropic?
Yeah, again, maybe this was quite fast, but both are fully isotropic at the scale of injection. TNG only in the time average sense, and also, I guess, Eagle in the time average sense, right? Both are a bit random per event, but in the time average sense, both are isotropic. Yeah. Okay. But the only cosmological simulation with the enforced well, sorry, Romeel, I'm going to say something wrong. Does SIMBA have bipolar? Horizon AGN is a bipolar AGN model.
Yeah, SIMBA's is purely bipolar, so stably bipolar. I think Celine actually had her hand up.
Yeah. So Celine, do you wanna comment on all of this?
Yeah, thanks. So I realize my name is not correct. I've invited my PhD student to be able to attend this very interesting session. So I'm excited to see a lot of discussion of this topic. I think, I agree with most of what I heard. So I just want to emphasize a few points. First, what Diane just said, right? So what we see is saying that, there's a lot of inflow and outflow and fountains, but in the simulation, both Eagle and TNG that have, different numerical and physical implementation of these processes. And yet, globally taken, there is a hint of an azimuthal signature. And I think we also looked at how this varies the number of parameters, and we've mentioned a few of them: redshift, impact parameter, phase of the gas. We have a cut in the temperature and current density, if you want, but also stellar mass, which I'd like to highlight because this is something that is very difficult to get observationally from the IFU data we heard about. And I think what's interesting is that what we showed is that the current observations that Jess is referring to are focusing on objects that may have only looking at one phase of the gas, or a more ionized type of quasar observer, or perhaps haven't dealt with the dust depletion issue in those metallicity measurements. And the point we're making is that we do need a significant sample of very precise quasar absorbers with robust metallicity measurements that are corrected for dust depletion, and with hopefully known stellar mass to be able to retrieve the signals that we expect from the simulations.
That's hard. The dust depletion is really hard.
Agreed.
One of the points related to this that was brought up in the Slack is the relationship between how much of this bipolar behavior in the outflows and in the distribution of the metals in the CGM is as a function of AGN feedback or supermassive black hole driven flows versus star forming driven flows. And do we expect a difference? I mean, I know, Dylan, when you were showing your models for this, you were saying, even with isotropic like deposition models, you'll intrinsically get anisotropic distributions simply because, the heavy column of the disk can channel these things out. So presumably in that respect, it may not matter as much if it's coming from an AGN isotropically or coming from stars isotropically. But someone also pointed out that what may be channeling things in a bipolar direction are cold gas structures on the scale of hundreds of parsecs that are presumably not resolved in the cosmological simulations and could be doing this. So how much of it is over-tuning, or how much of it do we need to actually resolve those structures? So all of these things, I think, play into, is it AGN? Is it a generic result of the simulations? I mean, what I'm getting here is that it's kind of a generic result, but it has to be teased out very carefully from the data sets, as well as the observations. But I don't know. Is that what people are suggesting?
So what we looked at quantitatively speaking is in the mass regime, where black hole feedback is not doing most of the work. which is to say this is a collimation of supernova type 2 driven outflows. And I think this is probably where observationally we can best go after the magnesium 2, right? As opposed to much more massive systems where black holes are going to be relevant. So actually I haven't thought too much about this in the context of, say, clusters or some other mass regime, this anisotropy of melicity or other observables, but yeah, maybe Chang-Goo, can you chime in about this collimation already from the smallest scales? All I can say is that, you know, as a thought experiment, this is what happens in simulations where we do not resolve such collimation on 100 parsec scale. So if it's also seen in reality, this is an argument that that is not the driver, but it's not necessary but sufficient. Yeah.
I mean, since Dylan called my name, I need to speak about this. But I think, I mean, based on my experience, I don't really have any answer for that because I'm always using this local disk type simulation. It always have a only the vertical direction there where the gas can escape. So it always blow things along the vertical direction. So yeah, I mean, maybe the point, I may want to just ask about this kind of the collimation happening there. Is it due to the disk that you already have? That means since the Filippo also raised this question about the existence of the disk, but you see that this bipolar outflow, does it kind of sign of does it kind of indicate that you already have a disk in quite large range of the redshift? I just wonder.
This was in essence our conclusion. I would maybe defer to Lisa if she's here and wants to say something about the emergence of the disk. I mean, emergence in the population sense of disks as a function of redshift, but again, I maybe want to steer us more towards the outflows if possible. But yes, this was our effective conclusion, that the collimation is a result of having the disk. And if there's no disk yet, then the outflows are not collimated, which is why redshift 5 and the gaseous bodies of most small galaxies are chaotic balls of gas and they're not thin disks. Then you have basically isotropic outflows. So this collimation comes hand in hand with the settling of gas into more thin structures, which prevents the flow, say, in the major axis direction. This was our rough interpretation, but could be refined.
I guess I could say something. I guess my feeling about this is that we might be thinking about this in the wrong way if we're thinking about, you know, how the outflows from the disk are, you know, creating an anisotropy in the metal distribution. I could believe that that's happening, you know, around specific types of galaxies where there's a burst of star formation or there's a burst of AGN activity. But at least in our models, you know, the vast majority of metals are deposited in the CGM long before redshift 0. So it's not that you're seeing an anisotropy that's associated with, you know, the way that outflows are being deposited now. The star formation rates are just too low. The velocities are very low today. Most of that stuff was put in there a long time ago. And as a result, I think when you see these sort of azimuthal dependencies, what you're really seeing is a dependence on phase, not a dependence on injection time or injection mechanism. It's which phase of the metals do you happen to be looking at when you look in the azimuthal direction versus the planar direction around a disk galaxy. And that's really a question of, you know, the dynamics of cosmological inflows and outflows and recycling and these sorts of things. So to me, that's how I think about azimuthal dependencies. It has nothing, it really has very little to do with, you know, what's going on with the galaxy right now, unless you happen to be looking like M82 or something like this. You know, other than that, it's really something that we have to interpret it within the context of, you know, sort of the phase structure of the CGM.
Okay. John?
Yeah, and kind of going along with the phase structure thing, one of the things that as an observer is kind of a little disheartening when Dylan talks about all of the mass being at 10 to the 7K. That's a very tough phase for us to observe and to characterize, and is likely a large issue for observers trying to quantify the mass of galactic outflows. But I was curious, last week in other talks, we've talked a lot about the interactions between phases. And so in these simulations, when you create an outflow of a given phase, doesn't matter what phase it is, does it stay in that phase? Is there phase changes that happen in different portions of galactic outflows? Is that important for the dynamics and the evolution of galactic outflows? And how can that kind of relate to our observations where we only have a very thin slice of phase space that we can actually characterize these things? So maybe this is, Chang-Goo and Miao and Romeel, this is stuff that you can talk about in different sort of simulations and how that might impact our understanding of galactic outflows like that.
Yeah, Miao and Chang-Goo, do you have a comment?
Yeah, I mean, I think it is a bit different. So I think what Dylan mentioned is basically the hot gas driven out by black hole feedback, AGN feedback. And what I think of the Miao and I usually looked at, it was the hot gas driven out by this supernova feedback. And in those cases, we usually see that their mass loading factor is still a bit low. It's not kind of the order of unity. It's a kind of the 0.1 or 0.2. But the main point we usually make is they really have a high energy loading factor. So, and they are really the responsible for hitting the CGM. So, I mean, I think, yeah, I agree that it is unfortunate that you may not really see those gas in observation very clearly, but definitely we need to have some handle on those phases to understand, not just to understand the total mass, outflowing mass budget. We really need to understand that, to really understand the energy budget there. So yeah, Miao can add more, yeah.
So in terms of those, for example, phase doesn't stay at its original state. Yes, certainly, I think that's many work has been looking into that. For example, the hot gas and the cool gas interaction. Therefore, there could be condensation and there could be evaporation. So in that way, together with this phase change, the metallicity also transition from one state to the other. And also for the hot gas, the hot outflow, they can really go much further than the cool outflow once you eject it out of the disk. And I think, you should also, those hot flow, they can also cause precipitation at very large radii. And then there, the metallicity would be, at least partly from this heavily enriched hot outflow. When you observe it, it already becomes cool.
Romeel and Dylan, do you guys have any comments? Based on the cosmological scales.
I think this phase exchange could be very hard for the cosmological simulations due to limited resolution. So frankly, that's where I would want to learn more from the idealized studies. I mean, if you see the kind of stuff which happens in very high resolution outflow simulations, then of course it makes you worry about the cosmological simulations with roughly, 20 to 100 times worse resolution in there, probably. So it may be a regime where we need more subgrid modeling to capture that phase exchange, or, well, first we need to know how important it is and when it's actually happening, and what regimes, and what distances around galaxies, of what types and what kinds of flows. I think, I'm not an expert on that, but if it's important, then it's probable, it's possible that, say, cool components of outflows in low resolution simulations are underestimated, of course, because we would have naturally crappier resolution that might be required to resolve some, say, cold entrainment or cold cooling in the frame of an outflow. So.
Yeah, I think this is the entire point of our physically evolved winds model that Shu-Yao and Neil and myself and others have been trying to put together. But yeah, Dylan's exactly right. I think we need to treat this as a subgrid problem in the phase exchange and the way that the propagation happens in relation to that, and the metal mixing, something that should be treated in a subgrid way in the cosmological models, which it's, I think, for the most part, not at this point.
That's right.
I just shortly comment that it's also even hard, it is also difficult in our type of the idealized simulation. Yeah, I mean the partial resolution is not enough.
Yeah. So justification for subgrid model, whether it's few, the one that you're involved with, Romeel, or there are a number of groups that are working on this, and I think it's justified. But okay, I've got a question.
Can we talk a little more about subgrid model, because I think that's a relevant question for everybody. Like, Dylan talked amazing. His great talk showed such nice evidence of like broad pictures, but he didn't get a chance to talk a lot about the subgrid models involved, and that's a big unknown right now. Can we sort of come up as a community some joint tests, or joint observational constraints that might help the simulators to constrain your subgrid models? What is the most useful thing for you, actually?
What's the most useful thing for the simulators?
Yes, from observational side. What would you want us to give you?
Well, okay. The thing I worry about, and I brought this up in the Slack chat, is tuning of subgrid models a little too closely. Obviously, we need to tie them to reality, but is there a possibility that we can overtune these models and have it ultimately be representing, like, hiding certain physical mechanisms or phenomena that, like, for instance, if you it was brought up in the Slack that if you have two like overtuned different models for different subgrid behaviors interacting, you might hide the presence of something else, whether it's cosmic ray behavior or magnetic fields, turbulence, something like that. Is this a concern? I mean, I'm concerned about this, but Romeel, Dylan, Miao, Chang-Goo, other simulators who are present, what do you guys think? Is this, it comes out in the wash, we shouldn't worry so much about this, or?
Well, I mean, I the way I look at it is I'm telling people like Miao and Chang-Goo what we need from a cosmological perspective, right? I have no idea whether it is cosmic rays or what that's giving rise to this, and I don't pretend to know that, at least directly from the simulations. So in that sense, I think you just have to sort of view this as sort of trying to meet in the middle. But yeah, no, I think for me, it's still a big problem as to how do we accelerate the bulk of the gas up to the sort of velocities that we need to, blow it out of the halo, and Dylan's exactly right that what you put in isn't what you get out, but nonetheless, even what you get out isn't necessarily what is predicted from the kind of simulations that Chang-Goo does or Miao, right? So I think there's still a big mismatch there. You can accelerate the hot winds to these large velocities, but that's not the bulk of the mass, and we need the bulk of the mass to actually be accelerated to these high velocities. So yeah, I don't know what the answer is, and I agree that that's still a gap that we don't know.
Other comments from the panelists?
Just a quick answer as to what we need from the observers. That's partially why I think outflows are so cool, because we've had roughly a decade or 15 years of galaxy simulations who've been carefully compared to galaxy properties. But never once, and really, have these kinds of simulations been compared to direct measurements of the baryon cycle, what the gas is doing outside of the galaxy. So that's why I think that with more sophisticated comparisons of what we can infer for outflows and also inflows, that these will be constraining the effective wind models in the subgrid physics even more than we can do by just constraining, say, the stellar mass content and the gas fraction inside the body of the galaxy, which has been the past general approach, right? So if we actually had a really strong determination of the radial velocity of outflows as a function of distance and stellar mass at 10 kpc, I'm sure you would already rule out most simulations, right? But I think there's a big gap there to make that comparison to make such a strong constraint. But yeah, I think direct outflow data is what we need to learn how to compare against it. But once we do, I think that's very interesting.
Good point. Good identification on what we need from the observers. Nir has been very patient and has a related comment to all of this.
Hi, thanks. So I guess this really plays off some of the comments that were just said, but I wonder if we want to try and constrain the different feedback models and differentiate between some of the very different assumptions that go into these different simulations, are we better off looking at the properties of the galaxy and or interstellar medium, or are we actually better off at looking at the circumgalactic medium? I thought that in terms of the stellar mass properties, basically all models were in good agreement. Annalisa pointed out to me on the Slack that apparently there are disagreements at the factor of 2 or 3 level, but I wonder, is that enough to really distinguish between the different feedback models given some of the observational uncertainties, which are also at the factor of 2 to 3 light level? Perhaps the CGM would offer much larger differences. And if the answer is yes, we should go to the CGM, what resolution do we need in cosmological simulations in the CGM in order to be able to effectively do this? And if all we wind up saying is, well, we can't do good resolution in the CGM, so let's add more subgrid models into our winds and into our CGM, like FEW, which I think is super cool, but again, it's another subgrid model. And then we're just subgrid model over subgrid model over subgrid model. How can we ever hope to break the degeneracies of the base level?
Excellent point. And this is the concern, I think. This is what keeps me up at night. Meta subgrid models that are too sensitive to the underlying layers that could cause artifacts that aren't real or whatnot. Comment?
Yeah, well, I have a response, but there's a lot of people who have their hands up, so I want to get to them.
Well, I'm wondering how many of the people with hands up are questions or comments related to this discussion, like new questions. I guess who's been waiting the longest? Ben Opp.
Shoot, I'm like typing in the Slack and the Zoom, and I can't even remember what I was going to say. But okay, I think what is really interesting is talking about baryon clearing. Like if AGN are actively lifting baryons out of pushing them out of the virial radius even, or at multiple like 10, 50 kiloparsecs in today's universe. And this is off of Tim Heckman's comments about that maybe not. But I do want to. I've been commenting in Zoom that there's this nice work by John Davis, spelled Davies, looking at Eagle and illustrious TNG and finding very different behaviors that both show an anti-correlation between the mass in the CGM at a given halo mass, like around 10 to the 12.5 halo mass, and SMBH. So like the more massive, the more that SMBH holds a record of the energy feedback. So the more massive the SMBH, the more energy has given to the CGM over its lifetime. And that's seen in, that's a prediction of both Eagle and TNG and probably others like Simba. And it'd be really interesting to look at that. But when is that happening? And I think in illustrious TNG, it's happening more in the later universe. Whereas you know, and I think that's an interesting question of whether there is this observed, can we observe this SMBH CGM anti-correlation, you know, just broad properties of CGM mass and SMBH mass, and two, when does it happen? And that's a big topic we're going to be talking about, I hope, this week and the next few weeks.
Jess?
Oh, well, now Ben starts talking about baryon retention fraction and baryon clearing, and I'm all excited. But I actually had a question going back to the previous discussion. Ben, I totally agree. I think that that's very exciting. And like from an observational level, I worry about, you know, constraining, obviously, the overall baryon content and by phase and things like that. I have a lot of thoughts about it. But the question is, just Dylan, in your talk, you had your slide early on about, you know, subgrid physical models and you know, how you derive them and how you implement them in the simulations. And you had something on there that was like talking about a preferred scale at which you implement them or something. There was some reference to a preferred scale, and I'm just wondering, like, what is that scale and how do you decide on it?
This is just a commentary on subgrid as a whole, not necessarily subgrid feedback. It even applies more generically, more straightforwardly in terms of a subgrid ISM model, as we call them, which is indeed related to feedback. But okay, so the point is simply that if there is a need to resolve certain things and not resolve certain things, for instance, you want to run a larger simulation, so you don't want parsec resolution in your ISM, then you want to make a dividing scale, which makes physical sense, so that you can create a physically well-motivated model for what's happening below that scale, which you can also implement in a numerically robust way. So I mentioned very quickly that the GMCs are such a scale in lots of current large volume simulations, right? It simply means that we choose, kind of not by choice, but we have decided not to try to resolve GMCs, right? That's one way to phrase it. So then whatever going on in terms of collapse on the scales of a few hundred parsecs and lower, this has to be treated in a different way, and different simulations do that in different manners. As soon as you break that barrier, and then you have to go much further, right? This is a fire model in some sense. As soon as you get rid of that model, you can't stop until you get down to a certain level of next level of realism or physics, which can then do some self-regulation in what is now a more complicated resolved ISM. So yes, these natural scales to break the models at, I think, are important to think about because they exist in every galaxy simulation.
Do you think that there's a natural, like an analogy in the CGM for those kinds of scales, like some kind of like cloud threshold size or something?
Yeah, maybe with the whole Starship, Mothership debate thing that was going on. So there could be. I think we need to answer that, but I would say it's entirely unknown right now. And it's really related to the existence of the super small scale structure or not, and if it does anything or not. And these, I don't think we have answers yet from the simulation side.
Evan has been waiting patiently.
Sure. This is kind of related to points that have come up in the discussion and also something Carter asked on the Slack, which is you guys have said that, you know, what you get out depends on what you put in, but I'm wondering about the degree to which you understand why what you get out is what it is. So Kartik was specifically asking about, you know, this relationship between outflow velocity and galaxy mass. And what sets that. And so I can see why if, you know, mass loading is higher for lower mass galaxies and outflow velocity is set by the ratio of energy injection to mass injection, then that would lead naturally to, you know, this velocity correlation. But I don't know intrinsically why mass loading is lower or is higher in your less massive galaxies. So I'm wondering, I mean, do you all understand that? Is there a simple answer that I just don't know?
Well, there's a very simple answer, and then there's more interesting answers maybe. The very simple answer is that just in terms of the simulations I know best, right? The TNG model, the velocity of an outflow at the injection scale is in model input. And we have a scaling, a linear scaling on the dispersion. It's actually a dark matter dispersion, which is simply a tracer of the potential depth, if you like. It's a tracer of the halo scale. So these lines were on some of the plots I showed, but I didn't have time to go into this. They showed, for instance, the expected velocity as a function of galaxy stellar mass of the model input, and then how that changes when you look at flows in different places at different times. So, for instance, to be more clear, we prescribed that the velocity of outflows increases with halo mass. Right? There's no other way to say that. We do that because we need such a scaling to reproduce the galaxy population constraints, like the stellar mass function. This is the whole motivation behind choosing certain scalings with certain parameters. That said, so once you have that kind of input in the model, a secondary correlation, like what I showed with respect to the star formation main sequence offset, which is to say that high star formers drive faster outflows, this is in no sense directly input into the model. And then we'd like to understand why does that secondary correlation with a different property come about. And there the answer can get more complicated, I think. And this is where the simulations get interesting to think about. Of course, the fact that velocity increases with galaxy mass, this is an input in some sense. But the details of that, so exactly what the velocity is at 10 or 15 kiloparsecs in a certain phase, that is not. That is a very interesting convolution of the input with the hydrodynamics and self-gravity and everything else which is being solved. I don't know if that answers the question.
Yeah, maybe. I mean, I think what I was trying to understand is the difference between the line that you drew on the plot that shows your velocity injection model and the velocities on that plot measured at wherever you measured them. They were different lines, and I was wondering if you understand why they're different. But other people can say whatever they have to say about it. But that's, do you understand my question?
Because the flows have evolved between where they started and where I measured them. Yeah,
right.
And
So
evolved
why?
Because at that point why?
Why did they evolve the way that they did?
Well, indeed, there's two answers. The first, my simple answer is they're simply evolved according to the coupled equations of hydro and self-gravity. Right? That's what we're solving. So hydrodynamical and gravitational forces slowed them down. That's why they slowed down. I don't know how else to say it. Of course, there's more interesting analysis to do in that question. Others comment.
Yeah, I think the details of its modification over time, sure, yeah, you can just chalk it up to hydro and the gravitational potential of the system, but it doesn't seem to me that that's an obvious explanation for like a discretized difference in behavior that Evan is pointing to here. I don't know. I just think.
What you mean, sorry, by discontinuous or discretized?
Well, no, I mean just separate lines for different systems. I agree with what you said, Dylan, but I don't think it's all figured out. I guess I think there's reason for.
Certainly not. That's...
Okay. Britt Lundgren has been waiting very patiently. Our final question for the discussion.
Thanks, Cameron. Yeah, I hate to be keeping everyone from lunch, but this also goes back a little bit in the conversation. But you know, when we were talking about different ways that simulators could test models with observations, what questions could we answer having to do with outflows? I think it would be. I think it's pretty clear from things Rongmon has pointed out, Nicola as well, and Xiao Wen in the Slack, that there are certain phases where we really are doing a good job of picking out the outflows, like magnesium 2. It's really clear that we can, at least in that phase, see the azimuthal, angular geometry of these outflows quite well. Over now a pretty large range in redshift, and the samples are growing. So I just wonder if, at least in that ion, if there's work that we could do to differentiate between Eagle and TNG, and different modes of feedback in the azimuthal geometry in particular at that ion. So that's kind of my question. Is there something we should be looking for in the radial extent or the opening angle or something that would help? Possibly not.
Yeah, I'm not sure I have an immediate answer to that
question.
As I said before, it was interesting that those two models return such a similar expectation for the metallicity dependence on angle in this particular regime that we looked at. I think there are many, many differences when you go further, but yeah, I admit I haven't thought about differentiating between those models, say, in terms of CGM observables. But I mean, you certainly can. Just to not answer your question about magnesium-2, let me mention oxygen-6. This goes back a bit to Nir's question about what data has been used, can be used outside of galaxies. I think oxygen-6 is an amazing example, right? We had this data set emerge from COS-ALERS. There was roughly 1 to 2 papers from every simulation which tried to compare to this data, and most simulations had big trouble to do so, right? With the generic, very generic conclusion being that calm densities, simulated calm densities of that ion were too low, very generally speaking. So I think we already have these kinds of interesting data sets, and magnesium-2 is another interesting example, which could be much, much harder for these cosmological simulations because of the lower resolution and the fact that some of this gas, particularly say in the outflow, could be emerging due to physics, which is not well resolved. But yeah, the oxygen-6 comparisons were a great example of this, and I think comparisons for the magnesium-2 and the angular dependence, these are few and far between right now. So it's kind of waiting for people to compare more in this space, in my opinion.
Yeah, just wanted to add on this conversation that the predictions will relate to metallicity, where metallicity is the sum of the metals of a hydrogen, right? So the magnesium-2 troughs are unfortunately often lack H1 information, right? That would be very important to get to a metallicity. And again, I would like to mention the dust effect that I think is, challenging to take into account in observation, but is important for these studies. So I agree with what Britt is saying. I think the samples are growing, and I'm looking forward to see more of these studies and in comparison with what the simulation are predicting and which of the different physical properties we can constrain with this new set of observations. Yeah.
Okay, we're a bit over time. Great discussion, lots of good questions raised. I'm sorry I didn't get to all the questions that were in the Slack, but hopefully over the coming days and weeks, people can glance over some of the things that were discussed there and comment on them. And we'll save some of these discussions for the next few days after Tim Heckman's presentation on Thursday, after some excellent tutorials tomorrow, one on mass loading by Evan Schneider, one on Voigt profile fitting by Marie Lau, and a really cool visualization tool, CosmoViz, that Joe Burchett will be presenting. And then Friday, we'll have obviously lots of time for discussion on these topics. So thank you to Dylan, excellent presentation. Thank you to our panelists. I think we got a really reasoned discussion with a lot of different perspectives on these topics. So thanks everyone, and continue the discussion. I'll copy and paste all the comments from the Zoom chat into Slack for reference. All right, have a wonderful day, everyone.